This set of slides is going to cover parts of Module 1, the Chemistry of Life, for the NAS2 review course. In this set of slides, I'll be going over parts 1 and 2, which covers atoms, bonding, and the properties of water. Let's start our discussion with the atom, which is the smallest unit or particle that has the characteristic of an element. An atom has a nucleus. Within that nucleus, you'll find a proton, which has a positive charge, a neutron, which is neutral, and then around that nucleus, in a cloud, you'll find the electrons. The electrons have a negative charge. Electrons circle that nucleus within a cloud, but in our discussions, we're going to depict them more as if they were circling in a distinct circle. It's just going to be easier to look at, easier to count the numbers of electrons. On the slide here, you see some of the common elements in biology: oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus. These are the ones we're going to focus on, but we will be discussing some of the other elements. Over here on the right side, you see helium. Now, helium is not found in biology. Helium, you're probably all familiar with because it's used in different balloons to make them rise. Helium has 2 electrons, and we see those depicted here orbiting the nucleus. Remember that electrons orbit the nucleus and they have a negative charge. Atoms have shells, and in those shells, the electrons that's where you'll find the electrons. So for helium, there's just one shell. We call that the valence shell because it's the outer shell, and it can hold 2 electrons, and helium has 2 electrons. One important thing that we're going to discuss in a bit is how the electrons that are circling that nucleus are going to determine how an atom bonds with another atom to make different molecules. Now for helium, there are 2 electrons, and for that particular shell, it only holds 2 electrons. Down here at the bottom, you see a depiction of the electron cloud model, and electrons do circle in very distinct orbits, but within these clouds. But for our purposes, we're going to simplify it and just draw discrete circles and put the electrons in there. This is your periodic table of elements. I've got a couple here within the slides. I'll show you a different table in a minute, but I want to point out a few things. One is it's daunting to look at all of these elements. Fortunately, for the purposes of biology, we don't have to worry about most of them. And I'm going to draw a line here right down the middle because we don't have to worry about pretty much the ones below this line. Okay, we can just forget about those. We're going to focus on the top half. Another thing I'm going to point out here is the symbols. Now, some of these symbols make sense. For instance, O up here means oxygen. That makes sense. C for carbon. That makes sense. Now, some of them don't make as much sense. For instance, sodium over here, the symbol is Na. Well, it's Na from the Latin word for sodium. Same for potassium. It's a K. It's because it stands for the Latin word for potassium. You need to know the symbols for the more common elements that we're going to talk about. Another thing I'll point out here, the atomic number. Now, each of these elements has an atomic number, and it's going to represent the number of protons and also the number of electrons. So for hydrogen, as an example, the atomic number is 1. So there is 1 proton and there is 1 electron for hydrogen. If we go over here, for instance, and look at oxygen, its atomic number is 8. That means that there are 8 protons and 8 electrons. And again, the number of electrons determines how these different elements interact with one another, meaning how they bond with one another, and how they create molecules. I'll point out another thing here, and that is this last column. We don't worry about the last column. These are called the noble gases, and they don't interact with other elements. We don't worry about those for biological systems, and I'll explain in a minute when we talk about bonds why they don't form bonds with other elements. Here's another periodic table of the elements, a little bit different colors, but I want to start fresh here and talk about a couple of other things. One is electronegativity. And we talked about electrons. Each of these elements has a draw on electrons, and that's called its electronegativity. Elements that have a low electronegativity tend to give up electrons to other elements. Elements that have a high electronegativity tend to steal or take electrons from other elements. Now, the lowest electronegativity is going to be here on the left side, and the highest electronegativity, with the exception of the noble gases, is going to be on the right side, and we're going to look at column 7 here for that. So that means, for instance, chlorine, okay, chlorine has a very high electronegativity, and it tends to want to steal electrons. But if we look over here at, for instance, sodium, okay, sodium has a very low electronegativity, and it tends to give away an electron very easily, and that's how we get sodium chloride. And I'll come back to this concept when I talk about ionic bonds and polar covalent bonds. But just to give you an idea of how these elements interact, again, it comes back to the electrons. Electrons exist in these orbits or shells. The outer shell is going to have a certain number of electrons, and it's the electrons in that shell that determine bonding characteristics. Now, how do you know how many electrons are in a shell? Remember the sequence 288. 288. The first shell has 2 electrons. And if we go back to hydrogen, which sits right up here, hydrogen has 1 electron. So that means that its outer shell has just 1 electron in it, and it has room for 1 more. If we go over here to sodium, okay, here's sodium. It has an atomic number of 11. So we put 2 electrons in the first shell. We put 8 electrons in the next one. So that's going to equal 10 so far. Its outer shell just has 1 electron in it. Sodium has a very low electronegativity, so it tends to give up that electron very easily. If we go over here to chlorine again, chlorine atomic number of 17. So we start putting electrons in shells. Again, you put 2 in the first, 8 in the second, so that we've got 10. And then you're going to put the other 7 in the outer shell or valence shell. Now there's room for 1 more. And because there's 7 already there, chlorine really has a big draw for a single electron, and it can steal it from sodium that's ready to give it up, and that's how we get sodium chloride through what is called an ionic bond. Again, we'll go to bonds. We'll go over bonds some more in a minute. Octet rule. The valence shell is the outer shell. The number of electrons in that outer shell is going to determine what types of bonds an element forms. And if you need to know how many electrons will go into the different shells. And remember the sequence 288. The first shell holds 2, the second 8, and the third 8. Now, as we get into higher levels of shells, and we don't have to worry about that for biology, there are some different numbers, but we're just remember 288. Now, I did this before with hydrogen. Here we have hydrogen. It has an H symbol. It has 1 electron, and here's that electron sitting there in its valence shell. It has room for one more. This is sodium, and I just went through that with you with sodium. Remember, sodium is Na for the Latin word for sodium. And it had 11 electrons. So you put 2 in the first shell, 1, 2. You put 8 in the next, 1, 2, 3, 4, 5, 6, 7, 8. So that equals 10, but it has 11. So the last one goes in the next shell. and there's only one in that shell, but it could hold 8. Okay, it could hold 8. But because there's just one, sodium really likes to give that away. This is carbon. Carbon has 6. Its atomic number is 6. It has 6 electrons. So you put 2 in the first shell, 1, 2, and then 4 in the next one. 1, 2, 3, 4. So to satisfy the octet rule, and here's the thing with this octet rule, elements are most stable when their valence shell has the correct number of electrons. And for every shell except the first shell, that is 8. And that's why it's called the octet rule. Atoms form bonds based on fulfilling this octet rule. And it may be an ionic bond, a polar covalent bond, or a nonpolar covalent bond. And we're going to look at each of these bond types. Now, when we talk about these bonds within molecules, within a molecule, we call those intramolecular. Sodium and chlorine form an ionic bond. And like I said, sodium, far left, it's on the left-hand side, very low electronegativity. It's only got one electron in its outer shell. And in this particular illustration, only the outer shell electrons are being shown. Sodium with this one electron will give that electron up to chlorine. Chlorine has 7 in its outer shell. It can hold 8. It wants to hold 8, so it's going to steal that electron. Now, in doing this, with sodium losing that electron that has a negative charge, and chlorine taking that electron, sodium now becomes positive, and the chlorine becomes negative. The positive charge and the negative charge now attract, and that's an ionic bond. So if you want to think about what forms ionic bonds, simple way to remember this: elements in column 1 and 2 and elements in column 7. Specifically for our purposes, think about chlorine. Most of the ones we're going to talk about is going to be something chloride, sodium chloride, magnesium chloride, calcium chloride. So here we have the sodium and the chloride ion. Once it takes on that negative charge, we call it chloride. The sodium lost its electron. The electron was negative, so now it has a positive charge. It is an ion now. And an ion with a positive charge is called a cation. The chlorine took that electron. It now has a negative charge. It is now an ion, okay, because it has a charge to it. It is an anion. So sodium chloride will form a lattice type structure, looks kind of like that. Well, what happens when you put that in water? Well, you put it in water, and the sodium and the chloride separate from one another. And the sodium remains a cation, and the chloride remains an anion. And here we see depicted the water molecules circling each of those ions. And I'll talk to you a little bit in a minute why the water does that. Ionic compounds dissociate in water to form ions, and if it's a positive one, it's called a cation. If it's negative, it's called an anion. Now, electrolytes, when we use the term electrolytes, these are ions that are capable of conducting an electric current. So when you put sodium chloride or salt, which is table salt, in water, it forms electrolytes. And again, back to the periodic table, just to review here. What forms ionic bonds? Well, ionic bonds, remember we're only looking at kind of the top half of the periodic table. Things in the first 2 columns, okay, with things in column 7, which is here. We don't see the 7 up here, but this is column 7. And specifically for our purposes, just think about chlorine. So we get sodium chloride, potassium chloride, magnesium chloride, calcium chloride. Again, things that are the elements on the left-hand side here, low electronegativity, the electron in the, or electrons in the outer shell get stolen, taken away by elements over here in column 7, high electronegativity, strong pull for electrons. Let's go on to talk about a different type of bond, a covalent bond. And we have a couple of choices here. It could be polar covalent or nonpolar covalent. In covalent bonds, electrons get shared. And remember, we're talking about the electrons in the valence shell or the outer shell. If it's a polar covalent bond, the electrons are unequally shared. That means that one of the atoms that's participating in that bond has a greater pull on the electron than the other atom. And I've written out here some of the atoms that we'll talk about that have polar bonds. So oxygen bonded to hydrogen, nitrogen bonded to hydrogen, phosphorus bonded to oxygen. Each of these atoms has a little bit different electronegativity, so one is going to pull those electrons toward it a little bit more. It doesn't steal the electron like it does in an ionic bond. It just pulls it more, and it's going to orbit one atom more than the other. If we look at water, which is a polar molecule, and there are many other polar molecules, the way we define polar molecule is if the majority of the bonds within that molecule are polar, then it's going to be a polar molecule. Water is an example. Glucose is another good example that we'll talk about. If we look at water, water is H2O, so there are 2 hydrogens and 1 oxygen. We've already said hydrogen has 1 electron total, okay? It only has 1 electron in the valence shell, it only has 1 electron total. So there are 2 hydrogen atoms here, each with 1 electron. It wants 2 electrons in that outer shell. The oxygen has 6 electrons in its valence shell, and really we only worry about the valence shell for bonding. 6 electrons, but it can hold 8. Remember, 2, 8, 8. So what it will do is it will form a bond with each of these hydrogens, okay, and a bond, go way up here to get that electron in. A bond consists of the 2 electrons, but because the oxygen has a higher electronegativity, it has a higher pull on electrons, those electrons that would normally be with the hydrogen spend more time with the oxygen. And we wind up with partial charges, and that's depicted over here on the right-hand side. So the oxygen, which has more electrons flying around its orbit at any particular time, has a partial negative charge, and we write that out with the Greek delta sign and a negative. The hydrogens, because those electrons are spending more time with the oxygen, have partial positive charges. This is what is meant by polar. A little bit difference in the 2 ends of the bond. It's a polar bond. Now, of course, we can talk about how water can mix with water, and we'll talk about that in a minute. But any molecule that we describe as a polar molecule, meaning it has lots and lots of polar bonds within it, it's going to be hydrophilic, or it will dissolve in water. And I have a slide in a minute that shows you how that happens. Non-polar covalent bonds. This is where the electrons are equally shared. Okay, atoms bonded to the same atom. Oxygen bonded to oxygen. That makes what we call molecular oxygen. That's what we breathe, O2. By definition, those 2 atoms have the same electronegativity. They're going to perfectly equally share electrons. Another couple of atoms that you don't really think about, but carbon with hydrogen. Well, they're different, but it just so happens that their electronegativity numbers are so close that they form nonpolar bonds. And I've put methane over here on the right-hand side. Methane is CH4. These electrons within these bonds here They don't get pulled one way or the other. They're pretty much perfectly evenly shared. It is a nonpolar covalent bond. So always remember that carbon with hydrogen, nonpolar. The thing about nonpolar molecules, they are hydrophobic and they will not dissolve in water. And this includes all the lipids or fats. All right, now let's talk about bonds that occur between molecules. So before we've talked about ionic bonds, we've talked about polar covalent and nonpolar covalent bonds. These were all intramolecular bonds. Now we're going to talk about intermolecular bonds, bonds between molecules. And there's a few different types of bonds that can form, but we'll, for now, just talk about hydrogen bonds. I talked to you before about water and the fact that the oxygen in water is a partial negative because the electrons tend to stay more around the oxygen, and the hydrogens in water are a partial, I'm going to try that delta sign here, positive. All right, so that's positive. Now this hydrogen down here is a partial negative. All right, well, you've got a partial positive charge and a partial negative charge between this hydrogen and this oxygen. That forms an attraction, and we call that attraction a hydrogen bond. This is a bond that forms between water molecules. And if you were to put a bunch of water molecules together, you would see a lot of hydrogen bonding. And we usually depict hydrogen bonds with a dotted line. So that's the dotted line there. You can see hydrogen bonds between all of these different water molecules over here. Okay, this is what makes water sticky. The fact that one water molecule has a hydrogen bond to another makes water sticky. And that's how you can get things like surface tension. Water kind of sticks together and holds things on the surface. Let's go back to what dissolves in water. And I talked to you about glucose. Okay, this is a common way of depicting glucose. Right over here on the left-hand side, there's a six ring figure here at each corner, with the exception of one. You're going to see a carbon. There are lots of different ways to write out molecules. This is just one. And within this glucose, we see oxygen bonded with hydrogen, oxygen with hydrogen, oxygen with hydrogen. Remember, I told you that oxygen bonded to hydrogen is a polar bond. Glucose is a polar molecule. Polar molecules dissolve in water, and this is why. If you were to put a bunch of glucose molecules in a beaker of water, the water molecules, and here they kind of look like a Mickey Mouse, this oxygen, which has a partial negative, will make a little hydrogen bond here to this hydrogen, which has a partial positive. These water molecules will form all around each of those glucose molecules, separating one from another. And that's why glucose dissolves in water. It's called a hydration sphere. So remember, bottom line, polar molecules, which include glucose and other carbohydrates, dissolve in water. Sodium chloride. Remember, that was our classic ionic bond between the sodium and the chlorine atom. Well, what it does in water, if you put salt, this is table salt, if you put that in water, the two ions separate. Chlorine keeps the negative charge here because it kept the electron. Because it's negative, it's going to associate with all of those partial delta charges. And the sodium lost the electron. That makes sodium positive, makes it a cation, and it's going to associate with all those partial negative charges on the water. And that's why sodium chloride also will dissolve, or we have a special word for that with ionic compounds, dissociate. So here's a little bit of a summary. Molecules with ionic bonds dissociate in water to form ions, either cations or anions. Molecules with mostly polar covalent bonds, like carbohydrates, which includes glucose, dissolve in water, and we say they are hydrophilic. Well, what about the nonpolar covalent bonds. Remember, nonpolar covalent bonds, things like carbon bonded with hydrogen, and that includes the lipids. These do not dissolve in water because they don't have partial positive or partial negative charges on them. Water can't associate with them in order to break different parts of that lipid apart. These are hydrophobic. Hydrophobic means it will not dissolve in water. Let's talk some more about water. Remember I said the properties of water are due to its ability to hydrogen bond with itself and with other polar molecules. Water, we call it the universal solvent because most things dissolve in water. Not everything, of course, but most things will dissolve in water. Water has a high specific heat, and there is a specific scientific definition for high specific heat. The bottom line is once you heat water up, it holds that heat very well because heating water up puts energy into it, and it's going to take a lot of energy to break the different hydrogen bonds that form with water. This is important because blood is mostly water. So in order to keep our blood at a good constant temperature, we rely on the high specific heat of water. High heat of vaporization, and again, there's a scientific definition for this, but when you sweat, that sweat will eventually vaporize. It takes a lot of energy for that sweat to vaporize, and that energy is going to be released as heat, and that's going to keep you cool on a hot day. And again, it's related to the fact that water forms hydrogen bonds with other water molecules. Solutions and concentrations. A solute is dissolved in the solvent. And we usually express concentration in milliosmoles. And here's the little abbreviation for that. And we refer to that as osmolarity. So the osmolarity just indicates the concentration of a solute in a solution. For instance, when I talk about sodium chloride, putting it in water, sodium chloride is the solute, water would be the solvent. Oftentimes we also use the prefixes hyper or hypo. So hyper osmotic means a high solute concentration compared to something else. Hypo means a lower solute concentration. Now, this has to do with the movement of water, which is osmosis, and the little figure down here depicts how water moves from one solution to another as long as the solute cannot move, and that's what the selectively permeable membrane is indicated. The solute stays on one side or the other. Because there's a high solute concentration over here on your left, the water is going to move in this direction. It moves to the higher solute concentration. And that does it for parts 1 and 2 of Module 1. The next set of slides will cover part 3 of Module 1, which includes acids and bases.